Good morning, boys and girls. Welcome to your first Extension 2 Mathematics lesson on the Mathematics channel. Thank you so much for joining me. Before we dive into today's lesson, I just want to have a quick chat about the topics we're going to cover in this course, whether on this channel or in the classroom. I'll have to wait and see. All right, so here is our journey through the Mathematics Extension 2 syllabus. So we're starting off today with the first topic called complex numbers. Complex numbers is quite a large topic, so we actually split up into two halves. We're going to do the first half over the next 5 weeks, and we'll do the second half the next term. For the second half of this term, we'll be doing a topic called mathematical proof. It's a pretty challenging topic, but it's super interesting. You guys are going to really love it. After that, we have 3D vectors, further integration, and further mathematical induction. Now, these three topics are all content areas that you are already going to be studying in the Extension 1 course, and we're going to extend them further in the Extension 2 course. So one of the best things about studying Extension 2 maths is that you kind of automatically are going to be more confident with your Extension 1 concepts that we're going to extend in quite a few of our topics. Okay, without further ado, let's dive into our first topic, which is called complex numbers. Today's lesson is just on the arithmetic of complex numbers. So we're going to explore what a complex number is, why we need them, and how I can do some algebra using them. Okay, before we get stuck into that, we need to talk about some different systems of numbers that you've already used in high school without sort of naming them. And we're going to look at a new number system we're going to work through today called the complex number system. All right, so the first system of numbers you would have used all the way back in kindergarten is the counting numbers, the numbers that you can count stuff with in nature. We call this set of numbers the natural numbers. So when we use this capital N that's been a bit hollowed out, this is us signifying the natural numbers, which is all the positive whole numbers. So if you want to solve this equation right here, you'll need the number x equals 3, which is a part of the natural numbers. Okay, then in year 7, you would have extended the natural numbers to include negative numbers. So the set that includes both positive and negative whole numbers, we call it the integers, and it's represented by a capital Z. So to solve this equation on the left here, we need the whole number x equals minus 3, so we need integers. Okay, if you aren't using whole numbers, you're probably going to be using decimals or fractions. So fractions are a part of a set called the rational numbers. So the set which is represented by a capital Q, which has been hollowed, this includes any number that can be expressed as two whole numbers in a fraction. So for example, the fraction 7 over 2, which we need to solve this equation, is part of the rational numbers. Okay, then in year 8 or maybe year 9, when you started to look at pi and look at surds, you were taught about numbers which could not be expressed as a fraction because they have no exact value, or they have no rational value. These numbers are going to be included in the set called the real numbers. So represented by a capital R, to solve the equation x squared equals 2, you need the value x equals root 2. Root 2 cannot be written as a fraction of two whole numbers, which is a theorem we're going to prove in a later topic, in our proof topic. So x equals root 2 cannot be written as a fraction, so it is what's called a irrational number, which is part of the set of real numbers. So real numbers encompass Q, Z, and N. This is kind of like a Russian nesting doll, pardon me. So the integers include the natural numbers. The rational numbers include integers and natural numbers because, for example, x equals minus 3 can be written as minus 3 over 1, so it's a rational number. And the real numbers encompass all of these three, as well as the irrational numbers. Okay, but today we are extending beyond the real numbers, and we're looking at numbers that aren't real, which are called imaginary numbers, part of the set of numbers called the complex numbers. So if we take these 4 pieces here, our natural numbers, our integers, our rational numbers, and our real numbers, and we include imaginary numbers, we now have a set called the complex numbers, represented by capital C. Okay, so to solve x squared equals minus 2, you need to be able to do the square root of a minus number, which cannot be done with real numbers. You need to use imaginary numbers. And that's what we're going to explore today. So to answer questions like this, x squared equals minus 2, we need to make up a new number or define a new imaginary constant. So we are defining I, lowercase I, to be the square root of minus 1. This is a function that we cannot perform with real numbers, so we're saying we're going to denote this imaginary constant to represent the square root of minus 1. That means if we had I squared, we would have root negative 1 multiplied by root negative 1, so we would have negative 1. If we had the number minus 4, we could write this as 4 times minus 1, and we could write the minus 1 as I squared. So minus 4 is equal to 4i squared. And more importantly, if we had something like the square root of -3, which we can't actually compute, but we can split this apart using our surd algebra and say that square root of minus 3 is square root of 3 multiplied by square root of minus 1. And the square root of minus 1 is defined by us as I. So we can write this expression as root 3i, or I root 3 if you prefer. Okay, so we can use this imaginary constant to turn an unanswerable surd into an expression that we can work with in some sense. If you're staring at your screen right now saying, why are we doing any of this? The short answer is that there are problems in real life that are so complicated, I suppose, that the easiest way to solve them is to turn them into a problem involving complex numbers, because we have a system of mathematics revolved around complex numbers that we're really good at using. So the short answer is that some problems are easier if you turn them into a complex number problem and you can solve them as complex numbers. So it's really useful in electrical engineering and a bunch of other stuff, but in this course we don't do our applications, we just do pure, beautiful maths. Alright, so if we wanted to answer a question like this, we're going to solve this quadratic equation. We're going to find the value of x that makes this equal to 0. Usually when you have a scary looking quadratic equation, you can't factorize, which this one can't be factorized. First thing we probably reach for in our toolbox is our quadratic formula. So we're going to do the same thing here. We're going to use our quadratic formula. So x equals -2 plus minus b squared minus 4 times a times c all over 2 times a. Alright, we'll do some simplifying here. So we end up with inside our what's it called, the discriminants, inside the square roots, we have 2 squared is 4, take away 4 times -1 times -5, works out to be 20. We get a -2 at the front and a -2 on the bottom. So inside our square root, we end up with the square roots of -16. And so when you solved a question like this in maybe year 10 or 11, you would have got to this point and you would have said that this part here is impossible, so we say no real solution. Which is true, there is no real solution, but there are some complex solutions because we can evaluate this using the power of I. Alright, so we're going to write the square root of -16 using our trick from the previous slide. We're going to write this as the square root of 16 multiplied by I. And now the square root of 16 is just 4, and so now we have some complex solutions. We can divide everything by 2 or divide everything by -2, and we're going to get 2 answers. So we're going to end up with 1 plus or minus 2i. So we get 2 answers, which are 1 plus 2i and 1 minus 2i. Okay, so like I said, no real solutions, but we have 2 complex solutions to this quadratic equation. So we can see here our complex number has 2 parts. It's got a real part, which is the 1, and it's got an imaginary part, which is the plus or minus 2. Okay, so complex numbers just don't have to be things with I, they can also have real components to them. Alright, so we're going to define a complex number as z equals x plus iy. So again, we got 2 parts, a part by itself and a part with the imaginary term. Okay, x and y need to be real numbers. The I part is the imaginary part. So the bit with no I is defined as the real part of the complex number, and the coefficient of the I is defined as the imaginary part. Okay, so a real part and an imaginary part. If we have the x part being 0, so we just have something multiplying with I, it's called a purely imaginary number. So for example, 2i is a purely imaginary number. If the y part is equal to 0, it means there's no imaginary part, you've just got a real number. So technically, even though a number like 5, for example, is a real number, you can technically say that this is 5 plus 0i, so it's a complex number, it's just real. So once again, the set of complex numbers also encompasses all the real numbers as well. It's just like an extension. Okay, useful fact here is that if we change the plus in our original complex number to a minus, or it could be vice versa, if that was a minus, this would be a plus, changing the sign of the imaginary part is called the complex conjugate of the number. Okay, this is important because it gives us some useful algebraic results which we're going to be using later on in this lesson. Okay, so the useful result is that if you take a complex number and you multiply it by its conjugate, so when we have that line above a number, that means the conjugate of the number. So the sign of the imaginary part, like I said, it just changes from plus to minus or minus to plus. Now, if we expanded these 2 brackets out using a binomial expansion, Or we could even use a shortcut, couldn't we? Because we have two things, one is plussing and one is minusing. So we can use our difference of two squares factorization. So we have x squared, take away, if we square the second part, we get I squared y squared. But now we have to keep in mind that I squared is an expression for -1, isn't it? Because I is the square root of -1. So if we have negative I squared y squared, we have negative y squared. So we have plus y squared. Okay, so what's happened here is that we've taken a complex number, we've multiplied it by its conjugate, and we've ended up with an expression that has no i's at all. So this thing right here is a real number. Okay, it's a purely real number. So you multiply a complex number by its conjugate, the answer will be a real number with no I terms. Okay, it's pretty useful. We'll see why later. Okay, here's our first two examples. We're working with some powers of I, and we're going to write these in a simpler way. Okay, so we know I is obviously equal to the square root of -1. That's how we define it. And once again, we said before that I squared is equal to -1. Now, if we took both sides of this equation and we multiplied left and right by I, we would end up with I cubed is equal to -I. All right, so the simplified version for I cubed is you could just write it as -I, which has got a smaller power, which is a little bit tidy, I suppose. If we took this I squared equals -1 equation and we squared both sides of the equation, on the left-hand side, we would get I squared squared, which is I to the 4. On the right-hand side, we would get -1 squared, which is +1. So anytime you see an I to the power of 4, you can simplify this by just writing it as a 1. And then the loop continues. I to the power of 5 would be equal to I, and then you go back rounds. Every 4 powers, you end up with just a 1. So if we want to simplify I to the power of 10, it's not too easy. It's not too hard. All we need to do is write it as I to the power of 4 times I to the power of 4 times I squared. The indices summed together make 10, so the maths all checks out. I to the power of 4 is just 1, and I squared is just -1. So we end up with 1 times -1. So I to the power of 10 is just a complicated way of writing of writing -1. There you go, simplified. Okay, similar trick for question B, a little bit trickier. We have I to the power of 2021. And what we really want to do is see how many I to the power of 4s are in here, because they're going to simplify into 1s, and it's going to make it really nice and neat for us. So what we're going to recognize is that, well, 2021 is not a multiple of 4, but 2020 is. So 2020 divided by 4 is equal to 505. So we're going to split this apart. We're going to write it as I to the 2020 multiplied by I to the 1. Now we're going to write I to the 2020 in a very clever way. We're going to write it as I to the 4 to the power of 505. Okay, if we expanded these brackets by multiplying the 4 and the 505, we would get 2020, so it all checks out. The reason we've done this is because, of course, I to the 4 is just 1. So we have 1 to the power of 505 multiplied by I. And 1 to the power of anything is always just 1. So we end up with 1 times I, so we have an answer of just I. So I to the 2021 is the same thing as just I. That's our simplified version. All right, groovy. On to the next ones. Just some basic algebra concepts or some basic notations. We have two complex numbers. This one's called Z. It's 3 minus 4i. We have another one called W, and it's 1 minus I. Okay, first thing we're going to find is the complex number Z take away complex number W. So subtracting two complex numbers, we have Z right here. We're going to take away W. We'll put it in brackets so we remember to negative both parts, both the real and the complex part. So expanding this out, we get minus 1 plus I. And now simplifying complex numbers, it's just like you're simplifying algebraic terms. We're just going to collect like terms. So we're going to group the real parts together, and we're going to group the imaginary parts together. So we'll have 3 minus 1 is 2, and we'll have minus 4i plus 1i is minus 3i. So it's just basic algebra as you would expect. Reals grouped with reals and imaginaries grouped together as well. Okay, for question B, we have minus 2 multiplied by W with a hat on top of it. So this means the conjugate of W. So if W is 1 and take away I, the conjugate is going to swap the sign of the imaginary part. So W conjugate is going to be 1 plus I. So we're doing negative 2 multiplied by 1 plus I. Just expanding like you would normally with brackets throughout high school. So we're going to have minus 2 take away minus 2i. There is w conjugate multiplied by 2. Okay, up next we have some more examples of working with algebra using complex numbers. So we have some bracketed terms that we're going to expand and simplify. So we're going to approach these using our standard binomial expansions that we've been using for a few years now. Only thing to be aware of is that if you multiply I by I, you get minus 1. Okay, that's the only trick to these questions. So for the first one, expanding out these parentheses terms, we're going to use a binomial expansion. So we're going to have 2 times 5, we're going to have 2 times minus 3i, we're going to have 5 times I, and then we'll have I times minus 3i. So the n term is going to be minus 3i squared, but then keep in mind that I squared is of course equal to negative 1. So we've got minus 3 times minus 1. So this n term is eventually going to be plus 3. Okay, we can group the imaginary terms in the middle by minus 6i plus 5i is going to be minus 1i. We'll put the 10 and the 3 together because remember the I squared is minus 1. And we end up with 13 minus I. There is our expanded and simplified complex number. Okay, for question B, we have 6 plus 2i squared. We're going to use a perfect square expansion. So we're going to have 6 squared at the front. In the middle, we're going to have 6 times 2i is 12i. We're going to double it to 24i. And on the end, we have 2i all squared. So we have 4i squared. Once again, I squared is minus 1. So this n term will actually be minus 4. So we have 36 minus 4 gets us 32. And we have the 24i as our imaginary part. And there's our expanded and simplified expression. Okay, up next we are dealing with the division of two complex numbers. So on the previous slide we did some multiplication. Question A, we have 8 plus 5i divided by 4 minus 3i. We want to express these with a rational denominator. I think that's meant to say a real denominator, but we're just going to leave it alone for now because I don't want to re-record this part. All right, so the way we're going to handle this is using the result that we looked at in a few previous slides of multiplying complex numbers by their conjugates. So the easiest way to simplify this fraction here in question A is we're going to take the top and bottom and we're going to multiply by the conjugate of the complex number on the base. Okay, so the conjugate here is 4 plus 3i. We're going to multiply that thing to top and bottom. So we're just multiplying by 1 essentially. Okay, the reason we did that is because as we saw, when you multiply a complex number by its conjugate, you end up with a real number, and that's what we want to have. We want to have a real number on the bottom. We want to have a rational denominator. Okay, so on the top, we're going to use our binomial expansion. So we've got 8 4s are 32. We've got 4 times 5i is 20i. 8 times 3i is 24i. And 5i times 3i is 15i squared, which will eventually be negative 15. On the bottom, using our difference of two squares, we have 4 times 4 is 16. Take away 3i squared, which is 9i squared. Which again, remember, 9i squared is going to be minus 9. So the bottom will actually be 16 plus 9, because the two negatives will make a positive. So like I said up top, we're going to have 32, and we're going to take away 15, because 15i squared is minus 1. So 32 take away 15 is 17. And the imaginary terms equal 44. On the bottom, we have 16 plus 9, so we have 25. And there is our expression with a rational denominator. It's also a real denominator. So there we go. If we wanted to split this apart, we could write it as two separate pieces. We could have 17 over 25 as our real part, and we could have 44 over 25 as our imaginary part. So sometimes the questions will specify they want you to split it up and write it as two numbers, a real part and imaginary part with an I. So you've got to be able to read. Okay, question B, we're going to do something very similar. We're going to take our two fractions and we are going to realize both of the denominators by multiplying by the conjugates. So we're going to take the first fraction, the 1 over 1 plus I. We're going to multiply top and bottom by 1 minus I, because that's the conjugate. And the second fraction, we're going to multiply top and bottom by 1 minus 2i. Okay, for the first fraction, we'll have 1 minus I on top, and on the bottom, we'll have our difference of squares. We'll have 1 minus I squared. Okay, so there's our first fraction. For the second one, we're going to multiply 1 minus 2i by 2 to get 2 minus 4i. And on the bottom, our difference of squares is 1 squared, take away 2i squared. So we have 1 take away 4i squared. Okay, now because I squared is minus 1, for this first fraction, we have 1 take away minus 1. So that gives us 2 on the bottom. For our second fraction, we have 1 minus minus 4. So we have 5 on the bottom. So we have 1 minus I over 2 plus 2 minus 4i over 5. And now we just got to combine these fractions. So we'll just do some cross multiplying. So we'll have 5 times 1 minus I plus 2 times 2 minus 4i over a common base of 10. And now we just need to expand and collect to tidy up and get our final answer. So we have 5 plus 4 is equal to 9. We have minus 5i minus 8i is equal to minus 13i. And our common base is equal to 10. So there we go. Usually when you're working with a fraction of two complex numbers, the question is expecting you to multiply top and bottom by the conjugate to make it easier to work with. So if you have a number on the bottom that's a real number, it's much easier to do algebra with real numbers than complex numbers. That's the idea behind it. Okay, example 5, we are solving an equation using complex numbers. We are trying to find the values of x and y. Given that x plus iy multiplied by 2 minus 3i is equal to negative 13i. Okay, first thing we're going to do is we're going to expand the left-hand side using another binomial expansion. So we'll have x times 2 is 2x. We'll have x times minus 3i is minus 3ix. We've got 2iy in the middle, and then we've got minus 3i squared y. Okay, minus 3i squared y. So that I squared, once again, will turn into a negative, which makes our n term equal to positive 3y rather than negative 3y. And what I'm going to do is I'm going to write the positive 3y out the front with the 2x. The reason I'm writing these together is because they don't have any i's with them, so they are real parts. I'm going to put the imaginary parts together. Okay, so I've got the minus 3ix just here, and the plus 2iy just here. Now, what we're going to do is we're going to write the real part in brackets just to sort of separate them. This is the real part of the left-hand side. If we factor the I out of the two imaginary parts, we get minus 3x plus 2y. Now, also on the right-hand side, I'm going to write negative 13i as 0 take away 13i. The reason I've done this is so that we can see that on the left-hand side, we have a real part of 2x plus 3y, and we have an imaginary part of negative 3x plus 2y. On the right-hand side, we have a real part of 0 and an imaginary part of minus 13i. So now the thing with complex numbers is that the left-hand side is only equal to the right-hand side if the real parts match up and the imaginary parts matched up. So from this third line, we can sort of extrapolate some equations and say, well, 2x plus 3y has got to be the real part of the other side, which is the 0. And the minus 3x plus 2y has got to be the imaginary part of the right-hand side. So this part must be minus 13. So we've got equation 1 is the real parts equal to each other, and equation 2 is the imaginary parts equal to each other. Now remember, we're trying to find x and y, so we've broken this problem down into a pair of simultaneous equations that we are going to solve. All right, I always like the elimination method, so what I'm going to do is I'll take the first equation and multiply it by 3, and I'm going to multiply equation 2 all by 2. So we end up with 6x plus 9y is equal to 0 for equation 1, and equation 2 will be minus 6x plus 4y is equal to negative 26. Now we have a 6x and a minus 6x, so we can add these two equations together, and we'll end up with 0x plus 13y is equal to minus 26. We can divide by 13 and we get y is equal to minus 2. Okay, now we pick any of these four equations and we substitute in y equals minus 2. Doesn't matter which one you pick. If you sub in y equals minus 2 and solve for x, you will get an answer of 3. So there we go. If y is minus 2 and x is 3, then this number multiplied by this number will get us an answer of minus 13i. All right, heaps of fun. Getting towards the end now. All right, we have a HSC question here from the 2019 exam. It's a band 2 question, so it's meant to be pretty easy relative to this course. We have two complex numbers, 1 plus 3i and 2 minus I. First thing I want you guys to do is to find z plus w conjugate And then part 2 is express z divided by w in the form x plus iy, where x and y are real numbers. All right, there's a chance for you guys to pause the video and see if you can answer this question by yourself already. If you're not feeling super confident, I'll go through the solution very shortly. Okay, here we go. So for the first part, z plus w conjugate. So we have z is 1 plus 3i. W is 2 minus I, so W conjugate will be 2 plus I. And now we simplify our terms, so we'll have 3 plus 4I, and there's your 1 mark. So it's basically 1 mark just for knowing what that little line above the letter means, which is not too hard. Okay, part 2 is a little bit trickier. We're going to write the two numbers as a fraction, so we have Z on the top and W on the bottom. And now we are going to write this in the form x plus IY. So once again, whenever you see a fraction of two complex numbers, 9 times out of 10, the question is wanting you to realize the denominator by multiplying top and bottom by the conjugate. So once again, 2 minus I is our number, so the conjugate is going to be 2 plus I. So I'm going to multiply top and bottom by 2 plus I. On the top, our binomial expansion gives us 2 plus 6I, and then we get I plus 3I squared. And on the bottom, we have 2 squared is 4, take away I squared. All right, once again, whenever you see an I squared, you're going to substitute minus 1. So on the bottom, we're going to get 5. And on the top, we'll get 2 minus 3 is minus 1. 6I plus I is 7I. And there we end up with our complex number. Now, this is not the right way to leave our answer because the question did say leave it in the form x plus IY. X and y are real numbers. So we are expected to split this fraction apart into 2 pieces and write minus 1 over 5 as the real part and 7 over 5 as the imaginary part. So 2 separate fractions for 2 separate pieces, the real part and the imaginary part. So that's what you need to have 2 marks as your answer. I'd probably say this answer might only get you 1 because there are no half marks in the HSC. Okay, that wasn't too brain bending, so we're going to finish off with a challenge question, which if you want to pause this and come back after you've had a go at the exercises when you are feeling more confident, it's probably what I would recommend, but here we go. We have Z plus W and ZW are both real numbers. Prove that either Z is equal to W conjugate or that the imaginary parts of both numbers are equal to 0. All right, cool, pretty big question. So where are we going to start? Well, we should start by defining what Z and W are going to be because we need to do some work with our complex numbers. So we're going to define Z as just x plus IY, so just a generic complex number. W is also going to be a generic complex number, but we've already used x and y, so we'll use A and B. Okay, now the question says that Z plus W is real. So when we do this complex number plus this complex number, we should have an answer that has no imaginary parts. So we have x plus IY plus A plus IB. So the way we write a complex number that has that's real is we write something in the real spot, but we know the imaginary part is going to be 0. Okay, Z plus W is a real number which has no imaginary part. Okay, if we once again group our real parts together and our imaginary parts together, we have the real part of the left-hand side is x plus A, and we have the imaginary part is y plus B. So from this, we can conclude that x plus A needs to be equal to m, and y plus b needs to be equal to 0. All right, so there's our 2 equations that we've extrapolated from the first statement that z plus w is real. Let's see what we can get from zw is real and see if we can combine them somehow. Oh yeah, worth mentioning that if y plus b is equal to 0, this means that y is equal to minus b. That's going to be important later on. Okay, so zw is real, so the product of our 2 complex numbers is also a real number. So we're going to have z multiplied by w is equal to, once again, a generic complex number that has a real part and it's got no imaginary part. Just using m and n as just any letters, you can use whatever you want. All right, expanding at the left-hand side using our binomial expansion. So we're going to have ax, we're going to have ibx, we're going to have iay, and we'll have, on the ends, we'll have plus I squared yb. I squared is minus 1, so I've gone ahead and written it as minus yb just to save some time. Okay, once again, we're going to group together our real parts and our imaginary parts. So our real part on the left-hand side is ax take away yb. Our imaginary part is bx plus ay. This is equal to n plus 0i. So once again, we're going to compare left-hand side and right-hand side and say, well, this means that ax minus yb has got to be the constant over on the right, the n, which we don't know what it is. And the bx plus the ay has got to be the imaginary part, which is the 0. So there are our two equations, and now the two on the ends are the important ones, okay? The m and the n we can't really do much with because we don't know what they are, so there's too many letters to work with. However, what we can work with is that bx plus ay is equal to 0, but we also know that because y plus b is equal to 0, that y is equal to minus b. So these two on the ends are the two equations that we're going to combine to try and prove these facts. So we're trying to prove that either z is equal to w conjugate, so x plus iy is equal to a minus ib, that's what we're trying to prove. Or that the imaginary parts, which is the y and the b, or they are 0. So we're going to see if we can prove those two facts using these two equations. Let's have a go. Okay, we're going to take the first equation and we're going to substitute it into the second equation. So where we see a y, we're going to replace it with a minus b. So the second equation turns into bx take away ab equal to 0. Okay, we have a common factor of b, which we can factor out. And now we have b multiplied by x minus a is equal to 0. So this gives us two bits of information. This means that, well, if this is a product with an answer of 0, this means that either piece could be 0. So one scenario is that b equals 0. And remember that y is equal to negative b. So if b is 0, then y equals 0 is also true, which is great because b and y are the imaginary parts of the numbers. And so if they're 0, that was one of the things we are trying to prove. So we've already done half of it. Okay, from this equation, b is 0, which means y is 0. So the imaginary parts are 0. Check, done. All right, the other possible scenario is that maybe b is a number, but x minus a is equal to 0, which gives us this answer. So if x minus a is equal to 0, this means that x is equal to a. Okay, looking back at our original equations, if x and a are the same thing, this means that z is equal to w conjugate, because we said that if these two things are the same and y is equal to minus b, then we've got the same complex numbers, but one's positive and one's negative. So we have z is equal to w conjugate. So we've kind of already proven it. So either we have b equal to 0, which means y equals 0, which means we've got two real numbers, or y is equal to minus b, and it's actually a number, but then we end up with x being equal to a, so the real parts are the same, and we have the two conjugate numbers. So there we go, proved. All right, sweet. So for you guys, I recommend ripping into the first exercise in chapter 1 from Cambridge. Here are some recommended questions. Or if you're not really vibing Cambridge, there are some questions in 2.2 from the Howard textbook that you can have a go at. I'm not saying you need to do both of these. I'm saying either of these would be good. I'd probably steer more towards Cambridge because it's probably some more challenging questions. But Howard's a good resource because all of his exercises have work solutions immediately afterwards. So they're really good for learners. But either of these will be good practice for you guys. Rip in and please let me know if you have any questions, and I'll catch you in the next video. Thanks heaps for watching.